Normally we don't have spring like this until like end of March. It's a little early. But still might swing back.
Yeah,
Is it supposed to?
say that.
Oh man. Keep the snow tires.
Okay, I think let's start. So, darling, are you recording?
Yes.
I think that should be okay. Yeah, today we are glad to have Dr. Deepak Ramasubramanian from EPRI. So, Dr. Deepak is a senior technical leader at the Electric Power Research Institute, and he joined EPRI in 2017, where his work is in the area of the modeling, control, and stability analysis of the bulk power system with focus on the impacts of large-scale integration of inverter interface generation and load. So he received his PhD degree in electrical engineering from Arizona State University in 2017. He is recipient of many awards, including IEEE PES Chapter Outstanding Engineer Award, Energy System Integration Group Excellence Award, North American Synchrophaser Initiative Outstanding Graduate Student Award, and Power System Operation Corporation Power System Award. So Dr. Deepak has done a lot in about the area of the inverter-based resources, and I'm sure today we learn a lot from him. So with that one, Deepak, back to you. So floor is yours.
Thank you so much, Saeed. So let me share my screen. So Saeed, there's some feedback coming from your end. I don't know if you have to mute your microphone.
Yeah, let me just mute that.
Okay, so this is probably better. So let me go back to slide share mode. If I can get it to work. Okay, great. So Saeed, just a quick question. I know you might have to unmute yourself again, but just to confirm again, you're able to hear me and see my screen, right?
Yeah, everything is perfect. Yeah.
Perfect. Great. Okay. So thanks so much again for the invitation. What I'll be talking about today is some of the work that we have done on trying to understand how battery energy storage systems could be used for system stability services in the future power system. A lot of this is guided by the fact that there is hundreds and thousands of gigawatts of battery energy storage system in the interconnection queue today. Now, just because a resource is in the interconnection queue, it doesn't necessarily mean it will be built. It doesn't necessarily mean it will be constructed and commissioned and deployed and operated. But because it's in the interconnection queue, it has to be studied. And that causes a lot of challenges. And anyway, we can reduce the amount of burden that is placed on the utility engineers and system operators is always beneficial. But that does mean that we have to look at performance requirements. It does mean that we have to look at the way these devices would operate. It does mean that we have to obtain some guarantees with respect to how they might function on the grid. And that's where some of the presentation today will lead towards. The material is covered by a lot of research work that we've been doing, and it's not just by me. There's a lot of collaborators who I have here at EPRI with me. And EPRI member-funded research has collaborated to a lot of this work, and then there are a few US Department of Energy grants that have also collaborated, contributed to some of the work that I'm going to be presenting here. So what are we talking about really? Essentially, we're talking about how the bulk power system is changing, how it is evolving, and how the needs that we expect for the system is changing with respect to inverter-based resource penetration. So you had the past system where you had a synchronous generator-dominated power system. And at that time, you actually required the inverter-based resources to pretty much do nothing on the grid. We wanted them to operate at unity power factor, and we wanted them to disappear as soon as an event occurred. Basically, we said that if a fault occurs, please trip. Please don't stay online. We want to take care of our system the way we know how to. So don't interrupt that or don't try to hinder the way in which we take care of the system. And that was the past. The way we are transitioning now is we right now want these inverter-based resources to do more. We want them to provide automatic voltage control. We want them to provide frequency response. We want them to provide better ride-through for different kinds of events. And we are requiring more and more of this because there are more and more of these resources in play. Now, when we are requiring these kind of services, it doesn't necessarily mean that we want them to behave the same way as a synchronous generator would. And that is more apparent when we go to the future, where we expect that an IBR-dominated system, we would require them to provide a lot of services to help maintain the system reliability without the synchronous generator being present. Now, this again doesn't imply that we want an inverter-based resource to mimic the operation of a synchronous generator. It doesn't imply that we want them to be only virtual synchronous machine or emulated synchronous machine or so on. That is one out of the many methods that are possible. But what we do want is that as we move towards an inverter-based resource dominated system, some of the services that we have gotten accustomed to, that we have gotten, it really helps us operate our system, those services that are provided by the synchronous generators, we do want these resources to be providing those services. The inverter-based resources, we want them to provide the service. Now, there is a nuanced difference between asking for an inverter-based resource to provide a service versus telling it exactly how it should provide the service. So we don't want to go down the route of trying to tell how it should provide the service. We just want it to provide a particular service. And that's where we're going to go towards with the entire topic that we're going to be discussing today. Now, if you want to look at this from the perspective of why are we discussing this so much, there are a lot of challenges with respect to how these inverter-based resources might have to provide the services in today's grid. So one might say that, okay, we have these inverter-based resources, we expect them to provide a bit of services and so on, but why is this important? Why are we discussing so much about it? And what are the real challenges that are involved here? So it's nice to think about this from a cartoon perspective. If you consider today's system, which is a synchronous generator dominated power system, then assume that it is like a wheel. It's of course not exactly a wheel, but assume it's like a wheel. And when you park a vehicle on an inclined slope, when you park it on a area of a region where you don't want it to roll down on its own, you put chocks on it, right? So you block the tires from falling down or rotating. Assume that you have that on the synchronous generator dominated system. So which means it's very hard to really move the system around. And if you have changes in injection that comes from an inverter-based resource, it's not going to be doing much in terms of being able to move the system around. Now, of course, here by movement, we don't mean physical movement, we mean electrical movement, which means that, let's say that the voltage magnitude, the angles and so on are changing. It's not literally having linear displacement or anything like that. However, if the system itself moved electrically, then any inverter-based resource that was injecting power would essentially look like something that is connected to it, and it would move with the system. Now, this kind of operation has been there ever since the first inverter-based resource connected to the network, probably around 20 years back. We didn't have any explicit terminology or name for it. Only recently, in the past 5 years or 7 years or so, we have started calling this behavior as grid following. So a label has been attached to a performance only recently. The performance itself was always there ever since the first inverter-based resource connected to the system. Now, this is in today's network. What happens in the future? So this IBR-dominated system in the future, still the same power network. It's still the same topology. It's still the same kind of network that we have today. But rather than having synchronous generators, you have inverter-based resources. What that translates to is this entire set of blocks that we had to prevent the system from moving around, that kind of reduces, because now you have a very nimble system. You have a very flexible system. You have increased elasticity, which means that if you have injections changing from these inverter-based resources, then they will cause the entire system that is there to move around. And not only that, when the system itself moves around, it will cause this inverter-based resource to move along with it. So you have this cause and effect electrical relationship that is now developed between these two networks. And this cause and effect relationship that is there, it can lead to an instability. It can lead to increased destabilization, especially if there is an increased cause and effect. And the reason behind that is, say this changes its injection, It results in the system changing its electrical profile. That change in the electrical profile causes this to change its injection, which again causes this to change its electrical profile, and so on. So there is a cyclic loop that is developed, which can become unstable. So this is kind of the challenge that we see for inverter-based resources to provide services. So the more and more services that we require from this particular resource that is connected to the grid, the more and more it can cause increased cause and effect loops to come about. And those increased cause and effect loops can have other consequences that we may not have prepared for. There could be an aspect of grid farming that can be a solution. So a lot of you are graduate students doing your dissertations and so on, and you might be reading a lot of papers nowadays that has the terminology grid farming. What I would implore upon y'all is don't follow a terminology just because it is a terminology. Try to understand what is the reasoning behind it. Try to understand what is the underlying principle behind it. Try to understand what it's exactly providing to the network, because there's a lot of times where terminology can be misrepresented. It can be misused. And one person who thinks about grid farming in a particular manner, the other person sitting across the table may not think about grid farming in the same manner, and that can cause a lot of misunderstanding. And it has happened in our power system. So if you want to attach a label with respect to how these devices can operate, then maybe such a resource can provide a solution for an inverter-based resource-dominated grid. But now let's broaden that field a little bit more. It's not just about grid following and grid farming. There's actually an entire spectrum of control that can be possible from these inverter-based resources. If you think about it, we said that the first inverter-based resource was connected probably 20 years ago to the transmission network. And over the past 20 years, every inverter manufacturer have improved their technology, have improved their offering, have improved their product, which means that the inverter-based resource that was connected 20 years ago is not the same as the inverter-based resource that was connected today. So maybe this terminology of just using grid farming and grid following is not sufficient. We can't really categorize just as two categories of resources. Maybe there's a broader spectrum that is needed. So we started coming up with these four categories, so to speak, or four subsets, if you think about it, going purely by the amount of services that these resources are providing to the network. So you have legacy inverters. That was the initial quintessential 20 years ago inverter-based resource that operated at unity power factor and provided no grid support services. Then you come down to the conventional inverter that actually does provide frequency and voltage response, but typically it provides it over a multiple set of seconds. It provides it at in a slower pace and provides it at a plant level. So any bulk power system connected inverter-based resource plant, maybe a solar or a wind, will typically have multiple units, will have multiple inverters, multiple turbines, and then you have a superarching plant controller that coordinates the response across these individual devices. It may have some optimization embedded in it, and so on. And that will control these individual devices and provide your frequency and voltage response over multiple seconds. Then you come down to something called an enhanced inverter-based resource, which is essentially an inverter-based resource where a lot of these services that were provided at the plant controller level are brought down into the inverter level. And because of that, you are able to provide full frequency and voltage response within 1 second of an event occurring. Now, there are requirements around the world that have now started asking for this kind of behavior, not necessarily in North America, but there are other regions around the world that have high inverter-based resource penetration that have started asking for these kind of fast responses. And what we've seen is, as a group, they can survive the loss of last synchronous machine. So maybe one inverter by itself cannot survive the loss of last synchronous machine, but as a group, they can survive, which means that 3, 4, 5 inverters together can survive the loss of last synchronous machine, which means together they are cooperatively being able to improve the stability of the network. And that is a drastic improvement with respect to any of these two categories above, wherein in these two categories above, even cooperatively, they couldn't survive the loss of last synchronous machine. So all of this is technology that has been continuously improved over the many years that inverter-based resource manufacturers have been deploying their products on the network. And then you have this future inverter-based resource that is also capable of providing black start services and can potentially single-handedly survive a lot of extreme events, which we are calling now as a future inverter-based resource. So if you look at these subset categories and you try to map them onto the previous terminology that we looked at about grid following and grid farming, what you would essentially see is it's a spectrum. You have grid following as one bookend, which would denote essentially an inverter that can provide nothing to the grid. And you have grid forming as another bookend that can provide all the idealistic characteristics that you want to the grid. And reality, everything would lie in between. So you have this continuum of control that goes from one end to the other, which does map towards different manufacturers continuously improving their products. It does map towards different manufacturers improving the way in which they deliver services to the grid. The other thing we have to keep in mind is when we talk about grid following and grid forming, often it refers to just a single inverter. But a plant that connects to the transmission network is typically made up of multiple inverters. So we have to be careful when we distinguish between response and characteristics of one inverter versus response and characteristics of the entire plant. Now, if we map this to where the world is today, or different power grids around the world are, most of them are still in this particular position. It could be either because they do not have that many inverter-based resources, or it could be because even though they do have many inverter-based resources, the regulatory requirements and the performance characteristics that are being asked for have not been updated, and there's still a lot of services that are yet to be provided. There are few power networks that use this capability. The Power Network of North America is one of them. Power Network of North America lies sometimes in between these two because you may not utilize frequency response capability for under frequency response from inverter-based resources. You might only utilize it for over frequency response because you don't want to curtail the inverter-based resource or dispatch it at a value that is lower than its maximum power point. And instead, you can only provide over frequency response. You do require a lot of voltage control right now at the plant level in most of the newer inverter-based resource plants that are connected to the grid. So there are a few networks that use this capability in the field that we know of. There are even fewer networks that utilize this enhanced capability that we have, essentially in terms of delivering this full frequency and voltage response within 1 second of an event. And there are only few island systems that are looking at this future inverter. So when you now talk about grid forming, grid following, as you all are doing your research work, as you all are talking to your peers, as you're talking to your colleagues, and so on, it's very important to identify where in the spectrum you are referring to a particular device, because that can help you identify how you should approach your problem and how you should approach your studies and work. So now, if we have this entire setup here, where you have a variety of spectrum of devices, and any power system at any point in time can have a mix of all of this. So for example, the power networks that are having this kind of capability right now on the newer devices, at some point in time required only this much. So there's a lot of inverters on their system that might have this, which at a further yet point in time, back in time, required only this. So at any point in time, you can have all of these devices on the network. And the challenge is being able to operate all of them together. The challenge is being able to allow them to operate together and cooperatively. And that's what makes our power system unique. That's what makes it work well. Because when you look at a power system, when you have gigawatts of inverters that are available in the present network who may or may not have some capability that is utilized. So think about it this way. You have a manufacturer, you have a power inverter manufacturer who, let's say, manufactures inverters for various networks around the world. They will supply a product to, let's say, Australia. They might supply a product to Ireland, and they might supply a product to USA. Now, they're not going to supply 3 different products to 3 different countries. Instead, they're only going to switch on and off capability within their products depending upon what they're being asked to do. So if Australia asks them for a certain set of services, if Ireland asks them for a certain set of services, and if the North American footprint doesn't ask them for those services, it's not that those manufacturers cannot do it. It's not that they don't have the capability to do it. It's just that they have not been asked to do it in North America, so they wouldn't do it. So that kind of aspect leads to a lot of underutilization of capability from inverter-based resources. So before we go down the path of trying to identify what else is required for the power system, what kind of new services are required from the inverter-based resources, it's important to identify what is being underutilized today. And if we utilize the underutilized capability, would it improve the system performance? Would it improve the reliability of the system? And would it lower the burden that is placed on the next inverter that is coming into the system? Now, I like to think of some of this from a sports analogy perspective. Not sure how many sports fans are in the room. But power system operation is a team sport. So I myself like soccer, like basketball, and so on. And those are team sports. You don't expect one player to always score a goal or shoot the basket and so on. You actually require the team to play together in order to win a match. And the same thing occurs in the power system. When every player, where every resource actually contributes a little bit in a beneficial manner, of course, then you can lower the burden on each player while still increasing the reliability, while still increasing the chances of winning. The entire burden ideally should not and cannot fall on just one player or the MVP, whoever that might be. So what we'll talk about in the next few sections and slides of this presentation is just talk about how we can utilize more of this capability that we have today in the network, in these inverter-based resources, and try to get an understanding that if we do utilize this capability, if we do ensure that we are making use of this underutilized capability, where does it lead us in the aspect of power system operation? So the services that we had spoken about previously, about how we're going to require more and more of them, we can categorize them into these 5 categories. We want fast and stable response. We want maintaining voltage. We need to maintain frequency. We need robust fault right through. And there is black start capability also. So we do need the ability to black start the grid in case there is the blackout. Now, out of these 5 categories that are there are 4 that actually require the resources to work together as a team. Because you can't expect, let's say, taking frequency as an example, you can't expect just one resource. You can't expect one source to be the frequency control for the entire grid. If we did that, then we would be using something like an isochronous governor control for all our synchronous machines, and then they would fight with each other. Or we would use isochronous governor control on just one synchronous machine and allow it to be the one to take care of everything. This corresponding example is something like a slack bus that you have in your power flow calculations, in your power flow solutions. You have something like a slack bus that can take upon all the losses and so on. But we all know that slack bus concept is just from a mathematical perspective, and there isn't anything like a slack bus in reality. So in the real power system, there isn't one source that is taking upon the entire burden to provide frequency control to the system, but rather you do have these resources working together. And we need to keep remembering that as we are going towards newer inverter technology, because it's not fair for the newer inverter technology to take upon the entire burden of ensuring stability of the system. The caveat to that is certain situations like black start, when you do actually need a couple of sources to take upon more of the burden, because black start by default, you'll have only 1 or 2 sources that are operating that can black start the grid, and they are the ones that will be able to take upon more of the capability that is there. Now, that is a nuance criteria. That is something that is that they are paid more for, that they are able to provide that additional capability, and they're not called upon to do it every time. So it is a nuance scenario that you are working towards. So if you do now make use of this additional capability, if you do make use of the fact that you have underutilized capability that you can leverage from these inverter-based resources, let's see what happens. So an example is some requirements around the world. So if you take a look at some of the requirements in National Grid UK or AEMO, which is the Australian Electricity Market Operator, you would see some requirements like this. So you have something called a dynamic containment and dynamic moderation service from an inverter-based resource, which is expected to be delivered within 1 second of initiation of an event. Of course, with some deadband settings and some droop settings. You have something similar from the Australian Electricity Market Operator, where they have something called very fast frequency control ancillary service, or very fast FCAS for short. And again, that needs to be delivered within 1 second, again with some droop settings. Coincidentally, IEEE 2800/2022, that is a standard for performance requirements for inverter-based resources, also has similar requirements for capability related to fast frequency response. Now, the mere presence of a capability doesn't necessarily mean it will be utilized, but we'll now see about what happens if you actually utilize some of this capability. So let's take a look at voltage control. So we spoke about how an inverter-based resource plant has many inverters in the plant. You have many turbines, many individual inverters, and then you have a plant level control or a coordinator that is really coordinating across these different inverters that is there in the plant. Now, if you allow all the voltage control, or if you apply all the voltage control, let's say only on the plant level, and you dispatch active and reactive power commands to each individual inverter, then when you have a step change of voltage, you would actually find that the response is a little bit sluggish, it's a little bit slow, it's delivered over multiple seconds. And sometimes there can even be a non-minimum phase response where the response goes in the opposite direction. Now, this is because there is communication delay. There is some amount of phase lag that is there between the plant controller and the inverter, and that results in this slow response. But rather, if you actually put some of that control or shift some of that control down to the inverter level, which is the utilization of capability that is available, then you can actually get a response that is delivered within 1 second. So you get a quick response, you don't get a non-minimum phase response, and you actually get a little bit of an improved voltage response or voltage control. So bringing about some of this fast voltage control at the device level helps improve some of the performance that we might see in the network. A similar thing occurs for frequency. So you have your original frequency control shown in blue, where you have everything at the plant level. You have the slower response that is delivered over multiple seconds. Now, for frequency, to a certain extent, you can retune, you can make the plant controller become a little bit fast, but because of the communication delay that exists between plant control and inverter controls, well, there's only so much you can retune before you start seeing oscillations come up, as shown by these oscillations on the orange curve. And then if you do shift it down to the inverter level, you do get a much faster response in being able to provide the frequency or the active power response within 1 second. So now you have gone from being able to provide this kind of a response in the blue curve to this kind of a response that you see in the green curve, and you see similar things in the voltage. So this utilizing this fast voltage and fast frequency response at the device level, what kind of impact would it have on the grid? So we tested that out on a few different networks. So let's walk through that. We tested that out on a microcosm system that can be representative of a lot of transmission networks that we see. So we see renewable energy zones where you have clusters of inverter-based resources connected to the rest of the network through long transmission lines. There's some load centers, and then there's few more resources connected all over. And then just for the fact that we didn't want to look at this from a 100% inverter system, we wanted to see a 100% renewable system, we added a hydro machine. And the idea was to see that if your battery energy storage system is able to provide this fast frequency and fast voltage response, and your non-battery networks provide the slower response, let's see what happens. There is a reason why we chose only the battery to be able to provide this, because there's a dispatchability aspect that you can leverage. There is a stiffer DC bus that you can leverage. There is better voltage control, energy requirements, and so on that the battery energy storage system will help provide, with the non-battery energy system network will not be able to provide, because you can't really dispatch it at a lower requirement. You can't really dispatch it at a, make use of the fact of obtaining headroom or anything like that. So let's see what's the response to different types of events that we would see. So you would first have a double line to ground fault that you would apply at 5 seconds, followed by a triple line to ground fault that you would apply at 7 seconds in this particular network. So first you see that we are able to get robust fault right through in this high inverter percentage system that is there, but not everything is going to be beneficial. There is a potential edge case that can come up where you could be triggering a voltage collapse. But the idea here is that with providing or with utilizing some of these additional capability that you had from these inverter-based resources, you are getting the robust ride-through behavior, you're getting the fast response behavior. If you want to look at it from a load increase perspective, we were able to see that you can go from a response that is something like this, wherein you have sluggish behavior to something that can actually control frequency quite fast around the nominal value with very little change in energy injection that was there. Actually, it was only around 10 kilowatt hours of increase in energy injection, which for these large batteries is pretty much nothing because they do have a lot of larger energy capacity that is there. So going from a plant level slow sluggish response, taking it down to the inverter level, utilizing the fact that the inverter can actually provide that capability does provide a improved benefit to the system. And that was on a microcosm system. So let's actually see if it works on a real network. So we did a study looking at the application of it in South Texas. What happened in South Texas was that they had a stability criterion wherein if they tried to increase the inverter-based resource percentage greater than 70% in that region. So the green curve at the back here is a stable response for a fault when the level of wind was 70%. Of course, it's a curtailed value, right? So if you have a 100 megawatt plant, it is curtailed down to 70 megawatt so that it is able to provide a stable response. And if that 100 megawatt plant went up to 99 megawatts, so to try to utilize its entire capability, then there were oscillations that were introduced by this blue curve. So we looked at different options, whether you have to look at it from the perspective of only reactive power, if you have to look at it from the perspective of only fast voltage control. And what we found out was both fast voltage control and fast frequency control was required in order to stabilize the network in this particular region. Whereas in another region of the network, for the same kind of N-1 event, but in another region of the network, only voltage control was also sufficient. It didn't require the frequency control. But if you didn't have either of them, you went into an unstable scenario as shown by the blue curves. So what this means is that by inclusion of this battery with fast voltage and fast frequency control, we could actually increase the amount of wind that was exported in the region by 1 gigawatt. So now, just by utilizing this additional capability, utilizing this capability that was not used at all in the systems that are there today, you are able to increase the hosting capacity of the network. You're able to increase the dynamic response of the network. You're able to increase the reliability of the network, which can then lead towards a 100% inverter-based resource system, or can actually lead towards weak areas becoming stable. And that can lead towards better utilization of the capability that we have. So then the next question comes up is, how does this really extend to 100% inverters, or how does this extend to further different types of weak areas that might be there on the network? So let's take a look at that. Let's take a look at a future scenario where you do have 100% inverters that are possible. We just want to recap some of this with respect to the terminology. So with the terminology, as we had seen before, we saw that there were 4 different subsets. We found that there was a spectrum of control that is potentially possible. It's not really advisable to bucket it into 2 different categories itself. And it may not even be advisable to talk about control. You might have noticed that I have not put a single block diagram of a control until now in these slides, and that is intentional. Because the idea of this kind of services from an inverter-based resource is that it should be control agnostic. It shouldn't matter whether I am running a specific type of control architecture, because as long as the type of service is provided, as long as the required service is provided to the grid, it doesn't really matter what kind of control architecture is used inside the inverter. So specific elements of control systems should not define the capability of a device, should not define the services of the device. And that leads to the question of grid forming. So what is really grid forming? How do you define it? Can you really take this ideal theoretical aspect that we have here and really define it from a control agnostic perspective? Is there a way to think about that? So there are some ways which we have been looking at it. There are nuances, of course, associated here. No one definition is perfect. But one of the ways we looked at it was, okay, let's try to define this across different time scales. If you have something in the subtransient time scale, you can say that grid following is more like a PQ bus in your power flow scenario, versus grid forming is more like a PV bus or a VF bus in your power flow scenario. Transient time scale, you can do both active or reactive power control, or you can do voltage frequency control. And if you go towards a steady state time scale, you can actually follow similar kinds of droop characteristics in both devices. You can also look at it from the perspective of what happens in the subtransient time frame in terms of whether it retains a current phasor or whether it retains a voltage phasor. But these are nuanced definitions that need to be treated with care. A lot of you who may have power electronics background may know that you can have a current source inverter be represented as a voltage source or a current source, and you can have a voltage source inverter that may be represented as a current source or voltage source. It completely depends upon how the control is structured and what kind of hierarchy provided by the control. So it's important to be careful when using such definitions and be very cognizant of the various nuances that are there with respect to defining these two different types of technology. Or you can go down the route of defining this from the perspective of performance. So this future inverter, that is what we had defined as one of the subsets in our terminology. This future inverter could be something that has a performance that can operate both with and without synchronous machines. It can operate with other inverters. It can positively contribute to load generation balancing, positively contribute to voltage control, has robust fault write-through, positively contribute to power quality, and positively contribute to system stability. Of course, all of this is so that all of this is as while meeting standard acceptable metrics that we have today, and of course within equipment limits. Now, of this, there can then be a subset of inverters that might be black start resources. Note that grid forming doesn't equate black start. Grid forming is not equal to black start. A synchronous machine today is not necessarily a black start plant. Not every synchronous machine plant is actually black start capable. You do need special equipment inside the plant to be able to become black start capable. So the reason why we, again, going back to battery energy storage systems, we said that it can provide a stiff DC bus, and we also know that there is strong DC voltage control that is possible, and there's gigawatts of battery energy storage systems coming in the interconnection queue that can potentially be leveraged to provide this improved capability and reliability to the grid. So now let's see. So we started seeing this 100% or weak scenarios. We started seeing the definition of a future inverter. We started looking at the performance requirements that we might expect from these resources. Let's see how does it line up in few example scenarios around the world. So we did a case study on an island network. Essentially, the idea was to try to understand how much percentage of this new inverter is required for the system. Should you require 20%, 30%? When does the system start breaking down when you have existing inverter-based resources? And what happens if you utilize more capability that is available in these inverter-based resources? So what we found out was that if your existing inverters, they provide no frequency or voltage support, so essentially legacy inverters, then in order to meet the under frequency load shed criteria, you would require around 23.5% of new inverter technology. But if your existing inverter's capability is actually utilized in a better manner, if you are able to provide fast frequency and voltage response from your existing inverters, then the percentage of your future inverter that is required goes down to potentially 7% or so. What is important here to understand is when somebody asks you the question, or if you're trying to evaluate how much percentage of a particular technology is required to maintain reliability on the system, it's important that you take into consideration what the other devices in the network are doing so that you can derive that percentage in relation to what else is happening on the network. Because if you don't take that into consideration, then that percentage does not really hold in a generic manner. We did a test in the southwest region of North America, wherein this was a local area, and we found out that there was again a stability constraint interface that didn't allow for inverter-based resources to operate at their maximum power point, but rather they had to be curtailed in order to be able to operate in a stable manner. And similar to the South Texas study that I had shown before, if you do add some of these battery energy storage as grid forming devices, we could improve the stability of the region, and we could improve the power transfer of the region. What's important here is that you can't add that to any bus in the network. You can't add this device to any location in the network. The location that you choose, the size of the device that you choose, all of that has an impact in improving the stability of the network. So which means that it's very important to be able to identify which location on the network is an effective location in order to improve stability. We had similar results from the southeast region of North America. Again, it was a similar kind of study to try to understand whether stability can be improved or not. And again, we found out similar conclusions that were available. Now, we did one effort in the Midwest region where we actually got a different kind of a result. This was a inverter-based resource plant that was being put in to replace a synchronous generation plant. So a synchronous generation plant was retiring and an inverter-based resource plant was being installed in that particular location. So the idea was to try to see in that particular location, if an inverter-based resource plant comes, what kind of performance does it need to have? And we found out that in this particular location, even if you made it quite weak, even if you made it with a synchronous condenser, they were pretty much very similar in performance. So what this told us was that maybe in an interconnected system, not every location is important. Not every location requires inverter-based resources to provide all grid services, which means even more care has to be taken when identifying, when procuring, when defining the different services that we might need from these inverter-based resources. Then we did a study on an international network. Now, of course, some of the visualizations that I'm showing here are not the actual Australian power network because they were confidential information. So it's a synthetic network that is showed for visualization. But what we did here was we had to understand across a 24-hour period, because the load changes. So you have light load at, let's say, 11 a.m. in the morning versus you have peak load at 7 p.m. in the evening. Across these different kind of loading conditions, we need to be able to maintain stability irrespective of what loading condition you see. And you have to have devices on the network that can help maintain stability across these variety of loading conditions. So we were able to find out, we were able to devise locations, we were able to identify the locations on the network, we were able to identify the size of the device that we had to really procure and show that if you do have that, then you can maintain stability across a wide level of loading conditions and so on. So just to bring everything to a close, just to recap, power system is a team sport. Power system operation is a team sport, and we shouldn't expect the burden to fall just on few devices. Actually, if every device contributes just a little bit, the benefits can be tremendous and the burden on each of them reduces. One way to do that is actually to improve the utilization of capability that we have in the devices today. You have fast voltage control and fast frequency response that you can improve its utilization, improve the capability that is there, and maybe battery energy storage system of their stiff energy source that is available. Now, this battery energy storage system can also provide black start and restoration, the MVP part that we talked about the services briefly, but that is a whole different set of nuances associated with it, which is probably a topic for another discussion later on, but it does have the potential to provide black start. Now, we do understand that a lot of the delivery of services that we're talking about here may have economic implications, may have market implications, but that doesn't take anything away from the technical aspect that is there. Now, just a little bit of aspect that I usually now put when I talk to an industry, when I talk from an industry audience to a university audience, is we are looking continuously to improve the engagement between university and industry. And in trying to do so, some of the things that we have observed, which might actually help maybe in the university curriculum, may help in your thesis work, in your dissertation work as you're using, is it's always beneficial to get more familiar with the commercial power system simulation software that is being used in the industry. There are 6 or 7 different software that are used just for dynamic studies. None of them are MATLAB. So it would be useful to get more insight with respect to the use of these commercial simulation software, get more insight, get more understanding on coding within these commercial software. A lot of these software offer the capability to code in languages like Fortran, EPCL, Python, but they're coded within the software. They're especially used to write up user-defined models within the software, and that kind of skill set is very much required in the industry from both the utility side, software manufacturer side, and many others. Also get an understanding on different kinds of inverter-based resource and load models that are there in these libraries. So you might learn a lot about round rotor generator model, classical generator model in your power system dynamics courses. And while that is extremely important, it's equally important to also understand the 10 or 15 inverter-based resource models that are there. There's a whole composite load model that is there in the software that are used day in and day out in the industry. They are used for a variety of studies. They are used for a variety of phenomena. They each have their own nuances that have to be understood because they can impact the system results that you might see. And finally, working with large networks, because while you might see something in a IEEE 3 bus system or a IEEE 9 bus or IEEE 39 bus system, which is informative, it experience with running 2000 bus, 4000 bus, 23,000 bus networks, and being able to debug, being able to understand why something is not running is a skill set that is extremely beneficial for the industry. So with that, Saeed, I'll close my talk and happy to take any questions.
Yeah, thank you very much, Deepak. That was very interesting topic. So first we go to one round of applause to Yeah, we lost our camera here, so I assume that you cannot see us. So for some reason, the camera stopped working. So, but hopefully you can hear us.
Yes, I can still hear you. No worries.
Okay, so let's first go to the people online. So if you have question, please go ahead and unmute yourself and ask your question. Anybody online? Okay, we can get back to the people online. So people in the room, yeah, go ahead. Yeah, go ahead.
So regarding getting IBRs to a state of being able to do black start, what is the biggest technical challenge we're seeing right now to get them to that point?
So the biggest technical challenge is being able to safely energize a transformer. So when you energize a transformer, you have a lot of inrush current that is drawn by the transformer. The magnitude of the inrush current and the characteristics of the inrush current depends a lot upon the remnant magnetic field that is there in the core of the transformer. It depends upon the saturation, the flux density, and so on. And that can have different characteristics. So now when you do energize a transformer with an inverter-based resource, such as a battery energy storage system, inverters are current limited devices, which means that they may not be able to provide the necessary charging current that is required by the transformer in order to be energized. And if it's not able to provide that necessary charging current, then it can actually result in a lot of harmonics being generated. It can result in a lot of voltage imbalance being generated, which can then make energization extremely difficult. So that is one of the challenges that is faced. The second challenge that is faced is a lot of times when you're doing black start, you are actually looking to start up one plant and then or start up one source and then use that source to start up the next source. Now, when you go from the first source to the second source, that first source is utilized to start up a lot of auxiliary load that is there on the second source. So every generation plant, be it an inverter-based resource plant or a conventional resource plant, has a lot of load in the plant facility itself. They can be cooling load. If it's inverter-based resource, a lot of it will be air conditioner load. Because in order to cool the inverter-based resource racks that are there. If it's a conventional plant, a lot of it may be motor load because there can be fuel pumps, there can be oil pumps, lubricant pumps, and so on. So this first source that has started up needs to be able to energize those load that is there on the second source. And energizing that load is challenging because when you try to start a motor or you try to start an air conditioner, it can draw a lot of current when it's going from the locked rotor state. So then being able to provide that current and provide that in a sufficient manner so that it doesn't result in an undervoltage scenario is where one of the challenges. So those are the two key challenges that come up in using battery energy storage systems for black start.
Okay, thank you, and great presentation.
Thank you.
Question?
Thank you for the great presentation, Dr. Deepak. My question is, so you mentioned how the siting of these BESS is very important in your grid, like when you studied for multiple like n-x contingencies. So I just wanted to know, like, while the reasons might be like more involved and would involve time domain analysis, I guess, but are there like any general thumb rules that, hey, if you place your battery storage system here, it would be better?
Yes, so there are some of that available. So in fact, for this particular study that we did use both short circuit metric criteria, and we used a criteria called remaining MVA. We have a report on this. I'll be happy to share the link later on to go more into detail. So we use that criteria as a way to identify which buses are actually buses that are needed or good locations. So it may be too small to see, but you see here that a legend shows there's a blue color which shows all the buses in the system. The yellow color shows all the generators. The green color shows of those generators which are inverter-based resources. And there's a red color that actually shows of those inverter-based resources, which was the one that we wanted to choose as grid forming. And there are only few red dots. The slide deck is available to y'all. Y'all can zoom in and see. There are only few red dots amongst all the green and yellow dots that are there. So we did use some steady state metrics to get an initial understanding of which location would be a candidate location. Now, of course, this can be further improved upon, because you can maybe have an optimization run done on this with respect to different constraints. You can look at different kinds of services might require different kinds of solutions or different locations. But at the end of the day, you have to come up to a common set of locations, because you can't keep changing locations depending upon the scenario that you're studying.
Yeah, thank you, Dr. Deepak. Yeah.
I have a question.
It seems that somebody is not. Oh, okay. Yeah, go ahead. Yeah, go ahead.
So I have a question, Dr. Deepak. So when you presented about the fast inverter-based control, you said that the response is like improved pretty much. So in that, do you mean by fast inverter control that you have controls like voltage and frequency loop on the inverter itself? Or
Correct.
What control did you transfer from plant level to the inverter level?
Correct. So it is voltage and frequency droop that is embedded at the inverter level, which is essentially previously it was, or in the conventional plant, it is at the plant level, and then we just transfer those directly down to the inverter level.
So does that mean it requires some kind of distributed control to maintain the voltage at the plant level?
Yes, so that is an extremely important point. So the plant level control will still have a voltage control embedded in it, but that'll be on a much slower time scale. So you do have to have that. You can't remove that voltage control on the plant level, because then otherwise you might have fighting that occurs between the inverters within the plant. So what you do is you do have terminal voltage control at the inverter level that provides you some level of response in the immediate time scale after a disturbance. And then you have a slower plant level voltage control that helps reset some of those controllers after a while in a slow manner once you have ridden through the disturbance.
So with this faster control, like, do you think there could be any new problems related with stability that was not seen before with the slow controllers in the system?
Yes, absolutely. One thing to note here is that fast doesn't always mean good. Fast control can actually result in instability for certain scenarios. And then it also relates to every control system, every control architecture can have stability issues. There isn't any one universal control out there that will never have stability issues. So it can lead to newer kinds of issues that might come up, which just means that we do have to study every kind of changes that we make on the system. We do have to be due diligent when we are carrying out those studies.
And last question. So you said for the fast response, the response time was less than 1 second. So does that mean it just consider all the communication delays and everything that happens between plant and inverter level control?
Yeah, okay, so that's the nuance there, right? Because it's put down to the inverter level, there isn't any communication delay that comes out. because you are responding at the inverter level. So whatever delivery of response that you're getting, and you're seeing that at the plant level, is the delivery of response that you're seeing at each of those individual inverter levels. So that communication delay that exists between the plant and the inverter is taken out of the picture.
So does this mean like this helps to overcome the issue with low inertia in the system?
It can. It can improve the stability of low inertia systems. It can improve the stability of weak systems. Will it always improve the stability of every system? That we don't know yet. That's where it goes down to there can still be scenarios that may have instability here, but as with any control system, that can exist.
Thank you.
More questions? We may have one last question. You want to ask a question? Yeah, you look, you want to ask a question. Go ahead.
This is not a super technical question, but as a student, I have a hard time finding resources. And the resources I'm talking about are like your model, your synthetic Australia model.
Mm-hmm.
What do you do to go about either building a large model that would take a lot of man hours to create, or where do you find big models like this?
Yeah. Okay. So this particular model that we have for Australia, synthetic Australia, we actually got it from a university in Australia in a project that we did with them. But that being said, if you are looking for large models, Professor Tom Overby at Texas A&M and his colleagues have developed a large variety of data sets. So if you just go to actually, if you just Google Texas A&M Power System Repository or something like that, you will actually get the link to that. And they do have a lot of synthetic data sets that are large networks.
Awesome. Yeah, thank you.
One more question? Okay, Deepak, we really appreciate your time and sharing very interesting and informative talk. So we really appreciate that. So with that, one more round of applause. Thank you.
Absolutely, Sai. Thank you so much.
Thank you. Hopefully see you sometime soon. Somewhere.
Yes.
I don't know where,
Absolutely.
but sometime soon.
Yeah.
Okay, have a great day. Okay, bye.
Okay, everyone. Thank you. Bye.
Bye.